Alright, now let's see if we can actually use some kind of tools to visualize these objects rather than just use our handy iterate function to iterate over things like this. Right? This is nice, but being able to see things is much more convincing. As they say, a picture is worth 1,000 words and all that. So the technique is not very hard. What we do is we draw a number line. A number line is a horizontal line signifying the relative positions of numbers from minus infinity to plus infinity. And depending on what you're using it for, it could be real numbers, rational numbers, integers, whatever. So we draw a number line from minus infinity to plus infinity, and we plot the orbits of points under a given function on the number line, and we can see patterns rather than just look at numbers and try to figure them out that way. So for this, I have a repository called it's on GitHub. It's got under the Lyceum nonlinearfunctions.git. You can go there and you can actually get this. So it's just git the nonlinear functions, and you can get it. So this is where it is. And the one we are interested in is this thing called linearplot.com. And you can clone it and use it. Any enhancements, patches welcome. It's supposed to be a simple tool just for visualizing. So it has a few arguments: win size, which is the size of the window. It has a minimum and a maximum, which is x into y. The win size is also x into y in pixels. The min and max are x into y for the coordinate. Okay? So you can, while the number line theoretically extends from minus to plus infinity, you can't draw it for that much. Just only a certain part of it, so you can draw that much. The function is a function to plot, and start is the point whose orbit we want to see. So let's just try a simple example. Python linear plot.py win size equal to 800, 600, minus min is minus 1, x minus 1. You don't need the y coordinate for min and max actually, but I put it in there so that we can scale the vertical size of the window using that. So minus function equal to Python syntax is eval internally, so and you have to use x as the variable as an assumption, which it makes, and you start at 0. Do this, you can see that it just stays there, and you can see a blinking thing in the middle. Put your mouse on top, you show the points. So 0 is basically a fixed point for x squared. How about 1? No, that's a fixed point too. It comes over here. We can increase this a little bit. Let's just so that we can see this. Let's make it 3x3 and 3x3. You can see 1/3 of the way. So this is 1, 1. Okay. Now you can make this 0.9, and you can see 0.999, and you can see how it falls down towards 0. See? It started over here, it went down, and finally it reached here. Now it's 0. It's staying at 0. It just keeps printing these things over so you can see it. Right. How about if we just go slightly above 1? You see it explodes, goes outside, and goes out of control. Finally the program crashes because it's gone. Alright, so this is fine. This is the way we use this. And I welcome you to try it out with different values and things like that. If you find, any suggestions you have on making it more robust or usable even, I welcome patches. So let's try messing with our logistic function and see what we get. The first thing we used was, I think, 0.5. All orbits tend to 0. So let's just do 0.5 into x into 1.0 minus x. That's our function. And let's start from 0. We'll plot it like this. The population will have to be between. So this should be enough. Then let's see what happens. So you can see that it's going down. It could be smaller and smaller and smaller and smaller, and like the number there, it's for all practical purposes this is 0. Right? So it's gone down. So, and this seems to be the case with things on the other side as well. It also goes down here. The next thing we tried was 0.8, for which also we saw that everything tends to 0. So 0.8 up to 0.999 comes down here. Same thing. So it's a very, very small value over here. Now let's try with 1. We saw that with 1 it comes down, but it comes down much more slowly. Right. Let's see this. Maybe if we reduce the size of the window a little bit, we can see that it's a -1. So you can see that it's over here, and it's not yet reached 0, but it just plays around. Now, now let's try the interesting things. We tried 1.5, for which we saw that it stopped. It tended to 1/3, 0.3. So let's see that. It went out from 0.9, it reached here, and now it's stuck over here, 0.3. You saw how it went up here. See? So this is actually an example of how this tool can be useful to visualize this. We then looked at 2 and saw that here in this case it goes to 0.5. So let's see what happens there. Let's reach the middle, 0.5. And so you can see that. Let's see what we got when we tried 3. It goes to 2/3, but very, very slowly. Let's see what happens there. So it's going around on both sides. We mentioned it oscillates between on one side and the other side of 0.666. And so here is 0.651. On the other side it's 0.679, and it's slowly tending towards 0.666, oscillating on both sides. There are other visualizations that make this even more clear, but even this is very useful. You can see how it's blinking on this side and that side. This is not periodic, right? It is actually converging on 0.666. It just takes a very, very long time to do it. Now, periodic points. Let's try 3.2. See what happens there. Well, 2 points. What are they? One is 0.799 and 0.513. So we can see the periodic points here. So now we have with 3.2 we were able to see a cycle 2 period. With 3.5 we were supposed to see a 4 cycle period. Let's see if that happens. Let's just let it run for a while. You can see 1, 2, 3, 4. So this is 1, this is 2, this is 3, and this is 4. 4 cycle period. You just keep blinking. How about with 3.55? This is supposed to see an 8 cycle period. However, the points might overlap, so you might not be able to see them clearly, but nevertheless. Maybe we can just expand this a little bit from 1.1. And the maximum was 0.8. If we increase this to say 1024, 768, maybe we'll have a little more resolution. See what happens here. So there's 1, that's 2, that's 3, that's 4, that's 5, that's 6, that's 7 here, and 8 next to it. So that's an 8, period 8 cycle. Alright. Now, with 4, this was another interesting thing which we saw. With 4, let's see what happens. There doesn't seem to be any pattern. It just, randomly litters the whole number, and you can't see anything happening. You can't see any patterns. You can't discern any patterns in this. It just keeps filling it up. Or keep fading out. This is, it almost looks random. Right? So this is what we said. With 0.4, with 4 as your ecological constant, it's almost impossible to discern any regular patterns. And finally, if we go beyond that, we said 5, it just goes to infinity. 0.1, boom. It just explodes and gets out to infinity. Alright? So this is a simple way of visualizing these kinds of functions. And I welcome you to use this program and see what you can use it for.